This is SI Sasha. Today we're going to look at this problem from chapter 6. This is problem 75. It is about flux, excuse me, electric flux due to a field. And we're looking at an open hemispherical surface. So about half of a sphere. There is no, what do I say? There's no cover on the bottom. So the electric field lines are going straight through the cap from the inside, like that. Yeah. So let's look at the formula first. First thing we got to say is flux is equal to integral E dot dA, where, as we've discussed at a previous SI, area has a vector. I want to talk about this for a moment because it's important for the context of a problem. Uh, It's important for the unit in general. Why are we assigning a vector to area, which is just, motionless, not really doing much? Well, we have to understand what flux is doing. If I have a field pointing up like that, you know, there's a charge on the bottom, positive charge, since the field lines are going away from it. Whatever. Some bar of charge, not important. There's a field here, and if I want to know the amount of field in some area there, well, I can draw a few areas, right? I could draw an area facing like that. I can draw an area facing like that. And I can draw an area kind of diagonal like that. So if you've ever seen a dream catcher or, just a solid ring of area, essentially what we're doing is we're taking this area, and we're dropping it in this field, and we're asking the question, how much area, or rather, I should say, how many field lines are you getting, comma, area, right? How do I know how many field lines are going through each of these areas, 1, 2, and 3? Well, first of all, for the sake of simplicity, let's say the radius is a meter. A meter, I think that's fine. The area of a circle is pi r squared. R is 1. You could just say pi, right? So the area here is pi, the area here is pi, and the area here is pi as well. Now, for the first shape, or we could start with the second shape. For the second shape, what we see is, if we look at it a little closer, this is what we have. All of these lines are going directly through the area. The area vector is directly up, fully aligned. Theta is 0 between the area vector and the electric field vector. The electric field goes up, directly up, positive j hat, you could say. And the area vector goes up, also in the positive j hat. So what does that entail for us? Well, if you're trying to capture the flow of water through a pipe, and you have a surface that's directly aligned with the flow of the water, you can say all of the water is being captured by that ring. The same way here, all of these flux lines are being captured by that ring of that area. So when you go and look at E dot dA, or even E dot A, right? Let's say we have a known area to be pi, E A, and when you take the dot product, you're saying cosine of theta. Now, because you have two vectors that you're dotting, you're asking, what is the angle between the two vectors? So in real life terms, when the angle between the two is 0, it means the area vector and the electric field vector are fully aligned, meaning you're getting all of those field lines. That's why when theta equals 0, cosine theta equals 1, the information encoded in this trig function is saying the more aligned these two vectors are, the more flux I'm going to capture. So here we just had EA, which is a full magnitude of E times A. Now, if we look at the second version, we have a sort of tilted area in that same field, And again, when you draw that out, something like this. Yeah? What are we saying here? We're saying that we have now an area at this angle. Let's say theta is 45. The area we are looking at is capturing a little bit less field lines than the one that's directly aligned because its area vector goes off like this, makes an angle of about 45 degrees with the electric field vector. So when you go to look at, well, okay, I know the area, E times A, cosine of 45 is radical 2 over 2. So that's the augment, essentially, on this, right? You're going to have some fraction of the magnitude rather than the full magnitude. Some of the field lines are getting captured, but not all of them. And that's essentially the purpose of this cosine term. Cosine is ascribing a value between 0 and 1 that's going to tell you how aligned these vectors are. That's the purpose of the dot product. Okay, the last example we can look at is, what if we're completely misaligned? Area vector is going out that way. Electric field vector is going up. The angle between the two is 90. Well, we say none of those field lines are going directly through the area like that. They're all kind of dodging around it and never going through the area directly. So when we look at EA cosine of 90, this goes to 0, everything goes to 0, and you say no flux. So once again, just to reiterate, purpose of the cosine is just informing us how much of the flux lines is this area capturing. Sometimes it could be a lot, in which case the theta, the degree between the area vector and the electric field vector, is very low. And sometimes it can be very little field lines because they're very misaligned. So, without further ado, we can apply that kind of logic to this problem. All right, well, now that we've looked at the purpose of dotting the electric field vector with the area vector, and we look back at the flux formula, which is E dot dA, I also want to look in isolation for a moment at what happens if there's a constant electric field. We say, okay, it goes out as a constant, and you just have this. This is essentially a fancy way of saying, what is the area of the thing I'm looking at, right? Let's say I have like a very weird area, something like this. Then this integral, where you're going to learn this in Calc 3, this will allow you essentially to find this entire area with an integral that goes through it, surface integral. And because I'm not here to teach Calc 3, well, I'll do a little bit of spherical coordinates in a moment. But for now, all you have to think about is, okay, well, that's usually just talking about the area in the problem. So in this case, for a circle, we're just talking about A of circle. For a square, A of square, and so on. We're going to be looking at relatively simple areas in these problems. Now, we're going to look back at this problem and see the area we're dealing with is not as simple as a simple two-dimensional area. We're looking at a open hemispherical surface. So in other words, the surface area of this semicircle, well, semisphere. So how do we represent that? First of all, once again, I'm going to draw this. Now I'm going to say E is going to pull out, right? Let's read the problem real quick. Due to the electric field, E is equal to E naught K hat. All that's saying is, okay, the electric field is going up with a magnitude of E naught, and it doesn't vary. So we have a uniform electric field, meaning we can pull E out of that integral. Then we say, okay, E and the surface integral of that shape. Well, we have a hemisphere, and the best way to look at this problem is in terms of spherical coordinates, okay? There is no simple two-dimensional area that we're looking at in this case. We're looking at a surface area that projects into the z-axis. So if we want to represent it, it's a very good time for us to understand a little bit more about spherical coordinates. So I'll draw a sphere in the z-axis, but essentially a spherical coordinate is just the equivalent of x, y, z, except instead of x, y, z, it's r, phi, and theta. Well, what does that mean? Well, let's look at the 2D plane for a moment. I can say I could go here, or here, or here, or here. I can go to any of those points in the two-dimensional coordinate plane, this being x and this being y. I can call this some r and some theta. This is some distance up this way, and it's some theta away from the x-axis. Same way this point right here is some other distance r and some other theta, and so on and so forth for each of these locations. Okay, so what's my point? You can have the same thing going on in 3D, right? We have these planes, and I can pick this point and say, okay, it's r, it's some distance r, it is some theta measured away from the x-axis, and it is also some angle down from the z-axis, theta, and this is phi. So for the context of spherical coordinates, from now on, I'll refer to the x, y plane as having an area, well, as having angles measured in phi, and this angle from the z-axis, angles measured in theta. An area that we can represent with spherical coordinates. It's just more convenient. You know, you have a point here, like let's say we zoom in on this hemisphere. We have a point located right here that you can denote by how far down from the z-axis, theta, how far out it is from the origin, r, which is constant in this case, and how much it's rotated about the x, y plane. So this could be going down here, for example, out here, and that is subtended by phi, and this is subtended by theta, and both of these are technically arc lengths, are they not? And when you have an arc length, you have some radius, or matter of fact, let's draw a circle. If I want to know the arc length here and here, well, this is also represented by some angle. Let's call it theta here. R times theta gives us that entire arc length right there. The same principle is going to apply in spherical coordinates, right? R times phi, oops, give us this piece, and r times theta will give us this piece. So when we look at the surface area, we can represent each piece of it, oops, by an infinitesimally small piece of area, like this. I know that's not that small, but you're going to have an arc length here and an arc length here. Length times length, area, yeah? So how do I represent each one of those little pieces? Well, a few things are going to happen here in terms of spherical coordinates. The first one is when we look at this infinitesimally small piece that you're kind of integrating through this entire hemisphere to capture each location, you're going to have this side, and this is going to be r theta, where theta is measured down from the z-axis, and you're going to have phi, which denotes how far about the x, y plane am I rotated. But the problem is, as you move up through this hemisphere, your bottom arc width, you could call it, is shrinking. Why? Because as you move up this thing, as you're taking that integral, let's start with a little piece, infinitesimally small piece of the hemisphere down here. Drawing it right here. Matter of fact, I'll make it red, right? That arc width at the bottom, r times phi, well, it's at its widest here at the bottom. And as you move this little piece up more and more, it's going to grow a little smaller, that arc width. And it's going to do that until you converge at a single point here on the z-axis. So that width is getting smaller and smaller and smaller. So when we look at that in spherical coordinates, the way you account for that is when you set up the first part of your integral, you're rotating about the xy plane because this is a hemisphere that is sitting on the xy plane and it has this circle as its bottom. You want to capture every location on that, and the way to do that is take it from 0 to 2 pi. Let's look at that hemisphere top down on the x, y plane for a second. You just have a circle. So if you have a shape that is rotated fully around like this, then you're going from theta or phi equals 0 to phi equals 2 pi. Same thing. You're getting all of this. So when you're thinking of taking a surface integral here, you want to revolve it fully around the z-axis. So that's the first part of your integral. And as I just mentioned, that arc width at the bottom grows narrower and narrower as you approach the point where the hemisphere converges. And that can be represented by r sine theta, d theta. Oops, excuse me, d phi. Now you're thinking, okay, why do I have a sine theta and a d phi? D phi, remember, is the angle from the x-axis here, phi. Again, we're looking top down on this hemisphere in the xy plane. It should be a y, it should be an x. And we're saying that we're going to capture all of that, so we're going from 0 to 2 pi. But what I just described, this arc width at the bottom, which is just going to be r times phi for every little section, well, the sine theta tells you that as I move closer and closer to this top, as the angle from the z-axis to wherever I'm integrating at grows smaller and smaller, the arc width grows smaller and smaller. Think of the sine theta term here as saying, at the very bottom, right, my hemisphere is going to have little areas with very wide bottoms. And as I move up here, they're going to grow smaller and smaller. So if the maximum possible arc width is at theta is equal to 90 relative to, let's say this is the xy plane, as I move up, theta approaches 0, which means sine theta approaches 0. So the very bottom, the highest that this arc width is ever going to be r times phi, isn't it? So r phi sine theta, where theta is going to be 90, that's the highest it'll ever be, or you should say r d phi. As theta, as your angle from the z-axis, the vertical axis, which the hemisphere is protruding through, as your angle to that grows smaller, that arc width on the bottom is going to grow smaller. That's why we have a sine theta term up here there. So let's look at our integral again. We have 0 to 2 pi r sine theta d phi. So we're revolving our integral to capture every part of this hemisphere. Going that way. Phi represents your angle in the y plane. Now to capture the z component, because remember, you have to move up. Somehow, you're moving up this hemisphere with infinitesimally small areas. The other part of that arc by arc section is this arc right here, which is defined by r, again, times theta. And because you're integrating through, you're not going to have the entire theta for every little section. You're going to have r times d theta. So in other words, r, and let's say this whole thing is theta, in just this example, this is going to be d theta. So this arc length here is going to be r times d theta. Excuse me, that angle is going to be d theta. So the arc length is going to be the radius times that little infinitesimally small angle, r d theta. So we look back at our integral, and we say 0 to 2 pi r sine theta d phi to capture the part of the hemisphere sitting on the xy plane, and we're capturing that as we integrate through. And the other part we want to capture is the r theta measured from the z-axis to get that side of the infinitesimally small areas. So we have another factor of r up here. This gets squared. And then we say the integral going from, now remember, how far does this hemisphere get from the z-axis? Well, this is 90 degrees. From up here to down here is a 90-degree angle, meaning our total theta is going to be 90, which is why we're going from out here. And remember, d theta is measured from the z-axis, so the farther down I go, the higher my angle. Here, theta is 90, so we're going from 90 to 0 as we move up this hemisphere and capture every part of it, which means that we want bounds of 0, excuse me, pi over 2 to 0. We have that factor of r to appear to account for the arc width. And we have a d theta appear to account for the fact that we're integrating. Okay, so this is our integrand so far. However, at the beginning of this video, I did mention one more thing is happening. E dot A. Okay, when we look at that hemisphere again, we know that a vector field, the electric field, is moving up through it like that. And we did say earlier that flux is just a function of how many field lines is my area absorbing. Well, let's look at area vectors again. For this hemisphere sitting in this plane, the area vector of this section right here is out that way. This section right here is up that way. And this section directly on its side is out that way. Here, the angle between that area vector and this flux line is 90. Here, it's somewhere in between, just another theta. And here, it's even closer to being aligned. And at the very, very top, the area vectors of this hemisphere and the flux lines are essentially almost fully aligned. So, how do I describe that with math? Well, we know that, again, we're starting here from the z-axis to the x, y plane. We're measuring an angle of 90 degrees. That's why we have the pi over 2 on that integral. And as we move up, like I just said, all these area vectors are getting more and more aligned with the electric field lines. So every infinitesimally small area is capturing more and more field lines the further up on this hemisphere you are. And the best thing to describe that is cosine theta. The less aligned we are, the less flux I'm getting. So when theta is 90, all the way at the bottom of that hemisphere out here, theta is 90, cosine of 90 is 0. And we're at the very top up here, where theta is approaching 0, cosine of theta approaches 1. So the last thing we have to do for this problem is we have to say, okay, 0 to 2 pi, 0, excuse me, pi over 2 to 0, r squared sine theta, cosine theta. The sine theta accounts for the arc width of the infinitesimally small section, growing smaller as it approaches and converges on the z-axis. Cosine theta accounts for the fact that each area vector is getting more and more aligned with the electric flux lines as you move towards this very top here, the z-axis. Okay? Area vector, area vector, area vector. More and more aligned with the electric field. So more and more flux is going on, and we say d phi because that corresponds to the first integral. We're revolving around the xy, and that's phi, d theta. This is our integrand right here, and this is what your integrand should be. So we can evaluate now. We can say, okay, well, we say the flux is E dot dA. I drew that backwards, but E moves out. And from here, you have that double integral, which we just described with spherical coordinates to be E naught in particular. We described that integral to be pi over 2 to 0, 0 to 2 pi, r squared sine theta cosine theta d phi d theta. Now, when we're taking an integral, first, we have to evaluate from the inside out. So we have this first integral with respect to phi. There is nothing to do with phi here, nothing to do with phi here, and nothing to do with phi here. So really, we can move all of those things out as constants, and we can say flux is equal to E naught times pi over 2 to 0, the integral of pi over 2, from pi over 2 to 0, r squared sine theta, cosine theta. Both of these are theta terms, so they're along for the ride with the d theta part. And then that is times 0 to 2 pi of d phi. All this means right here, this of course comes out to phi, right? Because the integral of dx with respect to x is x. So we have phi. All that says is I'm revolving around the entire xy plane to fully capture that hemisphere protruding out. So we go like this, theta, phi, excuse me, is 2 pi, and phi comes out to just 2 pi. So you get a factor of 2 pi, and you can rewrite that as 2 pi e naught really. Now the integral from pi over 2 to 0, r squared sine theta cosine theta d theta, and r is also constant. So we can move that out and say 2 pi r squared e naught integral from pi over 2 to 0 sine theta cosine theta d theta. And this from here is fairly simple. U equals sine theta, du equals cosine theta d theta. That accounts for every part of that integrand, so we rewrite it. And I'm not going to change my bounds because I'm going to revert everything in a moment, but u du, then you say u squared over 2. Now, plus c in this case, we're just going to omit. Can't tell you off the top of my head why, but there is no constant of integration associated with this problem. You get u squared over 2 from pi over 2 to 0, where u is equal to, as we mentioned up there, sine theta. And your final, but I had a little oopsie, but you get u is equal to sine theta, sine squared theta over 2, evaluated from pi over 2 to 0. Okay. Then we say sine of pi over 2 squared over 2 minus sine of 0 squared over 2. This goes to 0. Sine of 90 is 1. You get 1 squared over 2, which is just 1/2. So your final answer is E naught r squared 1/2 2 pi. 2's cancel, and your final answer is E naught times r squared times pi. And if we look at the book, that is our answer. Great. Now for part B, which I will show to be a little simpler. So part B says, if you rotate that 90 degrees about the x-axis, so you're making a rotation that looks like that, what is your new flux? Well, let's draw that. Now we have a sphere, or a hemisphere, that converges on a point in the y-axis. This is the x-axis. And all of the flux lines go in through this side and come out through that side. Now you're thinking, oh no, I got to do that whole surface integral again. Well, no, because look, all of these lines, these field lines, are going through here, going straight through, and coming right out on the other side. This is a symmetrical shape. So all the flux in on this side, all the way up to the halfway point, are going to start coming out that way. So the net flux is 0. Purely because it's going in through one side, coming out the other side, symmetrical. So your flux must be 0, which matches what the book says. So if there's any further questions about this problem, it's a little bit of a doozy, but if there are any further questions, let me know. Thank you.